Is it gonna start? Is it gonna start?
Oh, yeah.
Oh, we're live, Miss Wall. We're live at the Hive. Oh!
Bye, Miss Wall. Bye, Thomas.
Is that easy stuff from Friday?
That easy stuff.
No, who wants to take a calendar nap? Bryce can take a
And I got a good content. I thought I had more than this. I clearly had I'm gonna try and squeeze.
Brian! I feel we have to quiz today.
So you want to pop up?
I'm like, why are you looking at me?
Just box. Just box incident.
Rebecca, do you have lotion?
Alright, the opening that's on the board is review for our quiz today. See if you can't do it. What number are we on today? 10? We're on 10, that means we turn them in today.
I always lose the first one.
What do you want me to do about that? Why do you lose it? Can't you put them in a place you keep up with them? They're always.
All right, man.
What's up there, baby?
So, guess what?
I need the stool.
Like, so, man.
I'm so cold.
Oh, yeah, my.
I'm hard.
Oh, her? Yes.
Yeah. I'm gonna ask them what I'm using.
What?
On the.
Gabriel, I said Rebecca, Liliana. Now, High Road today, where's High Road?
He's not late.
He's not here. Jennifer, Eric, Linda, Ted, Bendon, I see him.
Yeah, he's here.
Where is he?
I finally saw y'all.
I see him in here. He's getting water.
It's real easy.
That's the Selma Price. That's the.
It's so easy.
Yeah, all of those. All of those.
Yeah, Emma, Fraser, Ellie, Brian, Alicia, Tim, Dylan.
I saw Dylan Saturday.
It's like miracle, there's all the two of us.
Oh, I thought it
Does that mean we win some money or something? Or do we celebrate?
No, it's a shot.
We can't celebrate.
No.
Ms. Wall,
Yes, ma'am.
did Bryce go to the media center?
Did who?
Bryce,
Yeah.
thank you.
Oh.
We need about 2 more minutes, and then we're gonna go over it.
What are you doing? Top 10 floor. No, not 60. Top 10 floor. Thank you, class. Top 5. Top 5 to the last.
I talked about.
Have you ever made it?
Oh, yeah, that's what I was saying too. One of my items to 12, so because then I was like, oh.
And then we start out with, and I go through my.
Liquid has such
I don't always make this. We talk about loss one. We get loss two. And then most of them see the pattern of either loss three. Okay, that's four, so, it's not even as game. And then most of them are like, okay, we can gain three, because, we're all back getting to eight. We gain three, get eight. We go game two, then game one, and then neither. And we were all okay with that. That was home break. We were good with that. Jerry, and then this one was removed.
Oh, attractive.
It's like so awkward. And right now,
Anybody.
so it comes so
And they seem to be okay.
And then
They seem to be okay with that.
and then
And
something.
then this one was very stable.
And then Zoe comes at the back, like, hey, that's gonna be like, no, like,
And I call this one moderate.
it's weird, because they don't
You know,
like,
it's like,
because it is something.
you know,
It's funny, it's funny, like, the whole thing is funny.
it wasn't. Yeah, I didn't want to explode, so I didn't want to, but I really showed it. And these we call fair. That's what I do. The middle is a protest. But basically they're saying, but that's what I did. It was like a 747 jet. We go back into that. The lost and gained, we were okay with. The number of out of shell and lost and gained, we were good. Was that very moderate, fairly, and didn't. I didn't have any more than I told you. Just look at it, throw out the columns, and when we practice. As long as we get that column. What was that column again?
You guys you can remember where you don't have to. Yeah, it was hilarious. I don't know stuff. But, you know what I mean?
I said, I literally just said 5 minutes ago. Okay, well, I have to come here.
I like replayed it. I'm like, ew. But she posted a video. Saturday.
It started from
Yeah,
here.
Sarah Brothers. She was talking to like. No, they're like, hey, mom. Lollipop or something else. Disgusting.
It started from here. There. It's cute.
All right, so question one.
What are the two?
Why are we going too fast? Where y'all at?
Isn't it backwards?
I'd rather.
Yeah.
Put that letter down.
Yeah, because I didn't give you a temperature, so just give me the letter. Because I
The
didn't,
eighth, no, the difference.
it's hard to line up the numbers, I have trouble.
The eighth.
Yeah, you're right.
You're right.
Because then I have to put that issue.
What did it say?
Backward.
I know. I told you, you had to be approved both ways.
Can we turn?
Yeah.
Well, I need to go across the court really real quick.
No, you don't.
Yes, I do.
No.
Why not?
Under my class, you don't.
Isn't it before?
No, no. No. We have a quiz, and this is review 4. Go over here and sit down.
Well, we're going with that?
No. Number 1, what is the freezing point? The letter, because I didn't give you any numbers. D as in dog? Is
Yes.
that what you said? Yes. All right, where is the liquid cooled at? A, B, C, D, or E?
E.
C.
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 E would be what state?
Solid?
E would be the solid. C is the liquid. And what is the boiling point?
D.
B is in boy, yes. All right, what is surface tension?
Boys that pulls together.
All right, a force that pulls together adjacent particles. What types of compounds have the best surface tension? All right, so what kind of compound is H2O? What's the word I'm looking for? All right, what is special about water? It is a liquid, but what's special about it being a liquid? I heard it out there. It's polar. Polar compounds. All right, what are the 2 types of solids?
Crystalline and
Crystalline and amorphous. And how do we tell them apart? There's 2 answers you can give me there. All right, so if one is fixed and geometric, how are the other ones arranged? Randomly. All right, that's one way you can describe it. What's the other way? Has to do with melting points. One has a what, Gemma? All right, which one melts over a range? Amorphous melts over a range, and crystalline melts at a specific definite melting point. Has a definite melting point. All right, and number 6, how are we going to calculate heat lost? All right, how do you know it's HF and not HV or the one with the delta T? How'd you decide, Emma? It says what? All right, it says heat, so that just tells us it's a Q. So how did you know it was HF though? It says freezes. All right, and what else is not in the question? There's not a change in temperature. Because there's not a change in temperature, we knew we didn't need this one. All right, so we knew we don't need that one because there's no temperature change. And because it said freezes, that's why Emma picked HF. So the mass is what? 35.6. And where do we find HF? And what is HF? It's what? 334. Okay, so we multiply those 2 things together, and what do we get? Anybody got an answer? Brought in my calculator.
He said 11,890.
All right, 11,890. And what unit do we put on it? Joules. All right, J for joules. Yep. Now, is that open in 10, Sarah Ellis?
No.
Yes?
Yes.
All right, if you will, make sure they're clearly marked. Make sure your name is on them. And then make a stack on my desk. Again, I will give you, if you're not one of the people turning them in, a couple days. Once I return them in a couple days, I will not take them late. Okay? So today's Monday. I'll probably hand them back about Thursday. Once Thursday arrives, I will not take them from you. So if you plan to turn them in, I need them by Thursday. That's 3 days. So if you know between now and Thursday that you're not going to do that, at least turn in whatever it is you have. Even if you only have 5. A 50 is better than a 0. Exactly. It's better than anybody's class. Yes, ma'am?
He's not here today.
That's just about reading the graph. You have the graph?
Yes, I do.
Okay, so whether it's going up or down, the highest point is always a vapor or a gas. The middle part is always a liquid, and the bottom is always the solid. Okay? So if this is a gas and that's a liquid, changing from a gas to a liquid, this is always going to be the boiling point. It's always going to be changing from boiling to condensation to evaporation.
That's B.
That's B. Or in this case, it's B. It doesn't matter what the letter is. But this line here between, this is a vapor, or stop touching it. All right, so this point right here is gas, right? This point is a liquid, right? So if that's a gas and that's a liquid, this flat spot is always going to be changing from a gas to a liquid. So that's always going to be boiling. It's always going to be evaporation. It's always going to be condensation because it's changing between a liquid and a gas. So if that's a solid and that's a liquid, this is always going to be melting and freezing because it's the point between the liquid and the solid.
Okay, but
So if I drew it the other way, which is what they're all complaining about, because the one we practiced in class went this way.
yeah, that's the one.
Again, that's a solid, that's a liquid, that's a gas. So if this is a solid and that's the liquid, that means what happens here? If this is the solid and that's the
It
liquid,
melts.
it melts, and what else does it do?
It freezes.
It freezes. And if this is a liquid and that's a gas,
It evaporates.
it condensates, it evaporates,
And it,
and it does what else? Boils. It boils, okay? It doesn't matter if it goes up or down.
okay, well then, how is it that? I was confused because it said the freezing point. Wouldn't it be D?
Because when it goes down, the gas is still here, the liquid is still here, the solid is still at the bottom.
And if it's the other way around, it's
The gas is still where? The gas is still at the top, the solid is still at the bottom. That doesn't change, okay? Now, did everybody see what Emma was asking me? When the graph is flipped, where's the solid at on this one? Where's the solid at on this one? At the bottom. That doesn't change. Where's the gas at on this one? Where's the gas at on this one? At the top. When you're talking about temperature over here on the y-axis, which state is going to have the lower temperature? The solid. So the solid is always going to be at the bottom of the graph. So the solid's at the bottom. The liquid is always where? In the middle. And what's always at the top? The gas. So if you remember your state changes, if the solid is at the bottom and the liquid is at the middle, what is always happening between a solid and a liquid? Solids to liquids always melt or freeze. Tevin, sit down. Liquids to gases always do what? Condense, boil, or evaporate. So if I flip the graph like I did in the opening today, if the solid is always at the bottom because temperature is at the bottom, what has to be at the top? The gas. So if you know gas to liquid again with your state changes, what has to be here when you change from a gas to a liquid? Boiling point, evaporation, or condensation. That doesn't change. So if you change from a liquid to a solid, what has to take place here? You have to either freeze or melt. Okay? They're just opposites of each other. But the state changes don't change themselves. Okay? Does that make sense? Questions? Anything else before we do the quiz?
Which audio?
You just need this paper.
Yeah, you get to use that. Yeah. The only thing you need the paper for are the Q formulas. The Q formulas are on the formula sheet, all three of them, and the Q for the heat diffusion, heater vaporization, specific heater on the front on the middle chart.
What was those things about like the crystalline?
Those are the two types of solids, crystalline and amorphous. Unfortunately, some of you might, but hopefully, this is an easy one. There's not a lot of stuff on here. Two types of solids.
I didn't take, and I didn't.
Wait, what is
You
it?
know what I'm saying?
Yeah.
I didn't take the two types of.
Solids, liquids, and gases, their properties, two types of solids, phase changes, the graph, calculating Q, kinetic molecular theory. What types of states have motion?
All of them.
At least you knew that.
Oh, does it start at Kinetic Molecular Theory?
Say what?
Does it start there?
I even made it multiple choice today.
Oh, thank you. Yes.
All right, so if you will, all right, you need your orange chart and you do need a calculator today. All right, you need your orange chart because you need your Q formulas and you need your heat of vaporization, heat of fusion, and specific heat.
Oh, okay.
Now, while I'm thinking about it, remember what I told you. This week I'm here Tuesday, Wednesday, and Thursday. Next week I'm here what day? None. Okay? So those of you who have missing work, missing tests, put it up to them.
Why are you not here next week?
My daughter has dance recital. We have tech week all week. I will not be here any afternoon. I'm in Thomasville every afternoon. All right? So, if you're gonna sit back there, I don't want all your crap up there beside you. Move that someplace else. All right? Because you're gonna sit back up here. You might as well leave all your crap up here. Yes, you need a calculator. I just said that.
I wish I was that smart.
I assume you're making it up. Okay. You're taking it, making it up. Alright?
Multiple choice.
Yeah, it's multiple choice. You're taking it, making it up. You're taking it, making it up. Taking it, making it up. You carry your quiz and still? Fabulous.
Well, I'm gonna make a nice cake.
You want to hear that?
Thank you.
That's the way did I give you one? That's that. Let me show you here. Must have given me one. Okay. I did that.
Well, look, you forgot we had school today.
Huh?
So I'm looking to go come to school today.
You thought I wasn't?
No, I wasn't.
Oh, well, it would have been okay, I guess, if you hadn't. We'd have missed you and seen you tomorrow.
You can't say. Yeah.
And there is a backside, for those of you who never turn a paper over, question 10 is on the back.
We're just going on to it, right, Mr. Walker?
Yes. Maybe you were still working at this point, were you? Here, Paul, this one, so grab your calculator and your word reference table. You have one? You guys sit at the table on the back. We're gonna be ready to move on probably before you're done. I'm talking to Ms. Baker.
Unless they push it out. But I'm gonna do the foundation. Same time. You going in 2 more days? I think they're here. But it's not right, it's wrong. But I agree with Tom. I talked to her before. She was on the computer. She said it was good. Burn. Yeah. Well, I don't think we're.
The first day. She just told me the virtual calendar, I just ended up with change. I don't get the country. With the new calendar, it was like, oh, she's okay, so maybe he would explain to me why the calendar is.
Monday. Yeah, I know. I thought this.
We wouldn't even have a place to furnish to sleep in. Exactly. You might have to be here all 5. What are we going to do for 5 days? Yeah, me too. All right, if you guys are done with your quizzes, pass them forward.
I'll try to figure it out.
That would be great.
I'll do the following.
Here's one, can I get some water?
Yeah, go ahead. And you guys can put your calculators up, because we don't need that anymore today. So when you're your goods, we move your stove.
I'll start.
All right. No, Trent can put it back in his pocket. We're not gonna start with that. All right, if you will, find your notes from Friday. Pen.
Oh, sorry.
Somebody else with you.
What?
I thought it was a water leak.
Yep. All right, so on Friday, we started talking about equilibrium ever so briefly. Yep, we talked about its definition. All right, we said equilibrium was a condition that had to have two opposing processes, right? And it had to have equal rates. Now, we also said that these two opposing processes could be physical or chemical. Now, I told you on Friday that we're going to do physical today, and in a couple days, we'll talk about chemical processes. Chemical will be a whole 2-day discussion on its own. We'll do a math portion of chemical, and we'll do, would you put my pipe cleaners back? Because I'm fairly certain you didn't come with your own pipe cleaners to class. You just took one that was perfectly straight. Now you've destroyed it, and now I don't want it. Sure, and now you owe me detention for taking it.
Oh, you detention?
Yes. So now you owe me detention just because you took something of mine and destroyed it. And you can do it after school instead of lunch.
Oh, yeah, you said after school.
I'll be here tomorrow. You can do it tomorrow. Instead of coming and interrupting my class. Now, I also told you we were going to do this with evaporation and condensation as opposed to any of the other types of physical equilibrium. We could do it with melting and freezing. We could do it with sublimation and deposition. But since the curriculum specifically calls for evaporation and condensation, that's the one we're going to do it with. Now, inside of this lovely box that I'm going to explain, we're going to use what's called a closed system. That means that the water inside of this box cannot escape. No outside conditions are going to affect this box. We're going to say the temperature inside of the box is 25 degrees Celsius, which would be a little warmer than room temperature in this room. All right, most of us would ask, Ms. Wall, why is the air conditioner not on? It'd be a little toasty for most of us. Now, inside of this closed system, we know the water molecules move. Okay? Everybody in here knows that. These water molecules in here move around. None of them are stationary because we're not at what?
Zero.
Absolute zero. Very good. Now, when the water molecules, and I'm going to abbreviate molecules MOLC just to save some space, have enough kinetic energy, they will break the surface of the liquid and become vapor. Okay? Now, I alluded to this last week when I told you we would talk about the difference between boiling and evaporation. So, if I'm saying that they break the surface of the liquid, what is the water beginning to do? It's beginning to whatever?
Separate.
Not separate. That's not the word I want to use. I said, I alluded to this last week. If the particles are beginning to break the surface of the liquid, what are the particles beginning to do? If they're changing into a vapor, what are they doing? They're not boiling, they're what? You can say vaporizing, but I'm actually looking for the E word. They're evaporating. Okay? All right, the water molecules are beginning to evaporate. All right, now remember what I said last week. When water evaporates, it is a non-boiling liquid. All right, that's why it always takes place at the surface of the liquid. When we get down here to boiling towards the end of class, this is one of the differences that I'm going to point out to you. Boiling can happen anywhere in the liquid. The particles can come from the top, the middle, or the bottom. But in evaporation, the particles always come from where? They always come from the surface. They always come from the top of the liquid. Okay? But, now, so these particles come from the surface. Now, if I ask you this question, are we at equilibrium?
No.
All right, I got a no over there from Sally. All right, tell me why. What's not equal?
Oh, no, it is. I think. I don't know. I'm just saying.
So I need to go erase and say yes. All right, somebody else. Are we at equilibrium? Someone wants me to erase and write yes. Yes or no? Betsy still going with no. Why, Betsy?
The temperature?
Do
they have enough
All right, are there two opposite reactions?
Yes.
What are they?
Water and temperature. The water.
What's happening inside the container? It's evaporating.
Oh, okay, I see.
That's one physical change. What's the opposite of evaporating? Is it happening?
No.
So do we have two opposing processes?
No. I know.
All right, so Salma was right when she yelled no. And the reason she's right is there are not two opposing processes right now. There's only one. The only one that we have so far is the water molecules are doing what? They're evaporating. That's all that's happening right now. So when we talk about boiling in a little while, when you first turn the water on the stove and it starts to heat, the only thing the water on your stove does is what? Evaporate. That will be important when we start talking about boiling in a few minutes. No. Y'all have all boiled water at the house. We're not going to put a pot of water on the boil.
Can we?
No.
Please.
No. No.
Wait, Miss White, you said it evaporates when you put it on the stove?
Yes.
Do we build a fire? I thought it did
What if you do
evaporate.
dry
I
ice?
thought it
When it first starts to warm, it evaporates.
and then
It doesn't boil until you see what happened.
bubbles.
There you go.
See, yes, I told you.
All right. So We have to draw 3 of these before you're all like, how many of these things we're drawing? We're drawing 3. All right, so we got our water molecule still in here. We got some vapor going on, right? All right, so water continues to evaporate. Now, if it continues to evaporate, what do we continue to build up here?
Pressure.
All right, that we are going to eventually create pressure. Yes, that's fine. But what are we making at the top of the container? Gas or vapor. All right, hold on. Y'all are jumping way ahead there. All right, so water continues to evaporate. Vapor collects at the, or let's say above. I don't like the way that sounds. Collects above the water. Now, we know that water is what? It's that word that I talked about earlier. Polar. All right. Polar water likes to do what? What does it do to other polar water molecules? They attract or stick together. All right. Polar water attracts sticks together, collects, and begins to condensate. Okay, so condensation begins. Are we at equilibrium?
Yes. Yes.
Are we at equilibrium?
Yes, because it's the ceiling.
All right. Now I've got yes. All right. So do I have 2 opposing processes?
Oh my God.
I got some yeses going on here. All right. If I look up here, I've got continues. Whoops, get over there. All right. Continues to evaporate. And I've got condensation begins. So I do have 2 opposing processes. Yes, I do have that. That's the second part of that definition. Equal rates. Did we say anywhere in there that the rates are equal? But I don't have equal rates yet. So, am I at equilibrium? No. Okay, not at equilibrium yet. All right, is everyone caught up who needs something off the board, or do I need to wait? Okay. All right, how about now? All right, so in our last box, this is the third one. I'm worried if you've already got 3. All right, so when is equilibrium going to be achieved is what we're going to talk about in this one. All right, so evaporation continues condensation continues. All right, so what can we say about equilibrium? When is equilibrium going to be achieved?
Why is arrows coming down now?
To illustrate condensation. I should have done it in the last one, I just didn't. Here, I can go back.
No, it's too late.
There, there's two arrows. All right, so what can I say there to illustrate that we have equilibrium? What do I need to write to say I have equilibrium? What's the piece that's missing? All right. When the rate of evaporation equals the rate of condensation, equilibrium is achieved. Okay? When the rate of evaporation is equal to the rate of condensation, equilibrium is achieved. Okay? When the rate of evaporation equals the rate of condensation, equilibrium is achieved. Are you with me? Huh?
I'm totally lost.
You're lost? Completely lost?
Yes.
Okay, that's fine. I need to know that. Can I go back? Everybody got what they need off the board so I can go back to the first one so I can help Jonathan? All right, tell me when you have it. Because we're getting ready to play with this with Le Chatelier's principle. What, Destiny? Le Chatelier is just a dude. His name's just French. All right, so if we cruise back here, all right, are you okay with the water molecules moving? Okay. When they move fast enough and they have enough energy, they will break the surface of the liquid. So out there on the street, it's going to rain this week. Puddles are going to lay on the road. When the water molecules have enough energy, they will eventually break the surface of the water and be given off. You remember talking about the water cycle in middle school, biology class? Same concept. The water is going to leave the puddle and become vapor. That's all I'm talking about here. When those particles have enough energy, they become vapor. Equilibrium is not achieved yet because the only thing that's happening in the water cycle so far is what? Is what? Evaporation. That's all I have. In order to have equilibrium, I have to have how many processes? And all I have going on right now inside of my container is what? Is evaporation. That's all I've got. So if all I have is evaporation, all I'm making up here is what? Is gas. I'm making vapor. That's it. Now, if I'm making vapor, though, that's where box 2 comes in. If I'm making vapor, all this vapor is collecting up here, right? What do we know about vapor or steam? It's just water, right? What do we know about water molecules? Water molecules are what? Hey, Ms. Floyd, what can we do for you today? Okay. What do we know about water molecules? They're what? They're polar. So if I'm polar and you're polar and Eric's polar, what are we going to do to each other if we get close to one another? We're going to stick to each other, right? So all these water molecules start sticking to each other. So if they start sticking to each other, we're going to start doing what? We're going to start to condense, okay? So in the water cycle, that's like we do what? That's right, water droplets, okay? So we're condensing back down into the water. So we said we're not at equilibrium yet, though, because we're evaporating and we're condensing, but did anywhere in this picture did I say we're doing it at equal rates? Until I say in the question, we're doing it at equal rates, can we assume we're at equilibrium? No. Until I say everybody hear me say this. Until I say in the quiz question, in the test question, in any kind of question, until I say you are at equilibrium, can you assume it? No. Okay? So if I talk about evaporation and condensation, unless I say you're at equilibrium, you can't make that leap. So all I said here is we have some evaporation and condensation going on. You have two processes, but did I say they're at equal rates anywhere in that scenario? Then we're not at equilibrium. So in this last box, we have some evaporation, we have some rain, we have some condensation going on. But until I say the rates are equal, you can't make that leap. But in this situation, I said what? They're equal. So in this one, you know what? You're at equilibrium. Does that help at all?
Yes.
Everybody else, does that help at all? Okay, so the last piece that I want to do with this is Le Chatelier. And we're going to bring him back when we talk about chemical equilibrium too. And you're going to really hate him when we do chemical equilibrium. Le Chatelier's principle. All right, Le Chatelier's principle says, if a system at equilibrium is subjected to a stress, the system will automatically readjust to minimize the stress. All right. If a system at equilibrium is subjected to a stress, the system will automatically readjust to minimize the stress. Now, there are three stresses that we are going to work with. One is temperature, two is pressure, and three is concentration. Now, today, the only one we're going to do is temperature. Pressure and concentration, we will save for chemical equilibrium. Bryce. Mhm. All right, if a system at equilibrium is subjected to a stress, the system will automatically readjust to minimize that stress. Now, again, we are only going to talk about temperature today. I will save pressure and concentration for chemical equilibrium. But those will pop up later in the week. All right, who am I waiting on to catch up?
P is pressure,
P is pressure,
and then
concentration. What do you mean, what's wrong with it? I have no idea.
no.
I couldn't hazard a guess.
Basically, saying,
Really has a like sharp in this that actually.
As well.
And she just like this shit is like crazy.
Oh my!
One of the lowest. Yeah. I mean,
I couldn't hazard a guess as to what that thing's doing. All right. So, what does that mean? Where did I put the pen? There it is. So let's say we have the same box we had just a second ago. Okay? And I have water in the box. And I changed the temperature to, I don't know, I had 25 a while ago, right?
Yeah.
Let's say I changed it to 55 degrees Celsius. I stressed my system at equilibrium, okay? It was at equilibrium. And I have increased the temperature to 55 degrees Celsius. How does the system respond? Okay. So I was at 25 degrees Celsius, and I have just done what to this trusty system? I increased the temperature to 55. So what is going to happen?
It's gonna evaporate faster.
Okay, most of you can answer this based on what you already know. Most of you can tell me that it is going to, the water will do what? What did Brian just say? It's going to evaporate faster. The water is going to evaporate faster. So if the water evaporates faster, what are we going to make more of up here? Hold on, before you get to the condensation, what are you making more of up here? Making more water vapor, okay? So you make more water vapor. All right, so if we make more water vapor, then we get more what? That's right. So you get more condensation. So essentially, if you're going to evaporate faster and you're going to make more condensation, what's happening to your rates? Are your rates getting faster or your rates getting slower? You're faster, okay? So your rate of evaporation is faster. So your rate of condensation is faster. So, can we get back to equilibrium? Is it possible? Yeah. Okay. Equilibrium. Let me change colors there. Equilibrium is reestablished when the rate of evaporation equals the rate of condensation. The only difference is now it's going to happen at a what? A faster rate. That's the only difference, is the rate will be faster. It's still going to get back to equilibrium, it's just faster. Now, what would happen if I lowered the temperature? Catch up with me and I'm going to ask you about that, because I know lots of you are still writing. All right, you caught up? You're not right. Yep. All right. You're speaking for the other people. That's very nice of you. All right, so what happens if we lower the temperature? What do the water molecules do? They slow down. So what will happen to the rate of evaporation if they slow down? The rate of evaporation will slow down or will speed up?
Wouldn't it stop though? Like, cause you know, wouldn't it be more condensation than evaporation?
So you think the rate of evaporation is going to stop altogether?
I mean, no, I would probably stop, but I feel like it'll slow down over time.
It will slow down over time. All right, so if evaporation slows down, what happens to my amount of water molecules up there that become vapor? Will the vapor increase or decrease? It will decrease. So if I have less vapor, what happens to my rate of condensation? It'll decrease. So what happens to my equilibrium?
It disappears.
I can't have equilibrium ever again.
Well, I mean, you could.
I will, but what happens to my rates? If all I have to do in my sentence is, I will have equilibrium when the rate of evaporation equals the rate of condensation, but my rates are going to be what? Slower. That's the only thing that's going to change. Okay? See if we can answer some questions here. Where's my sheet? Right there. Remember, this is important for understanding how boiling works. Because boiling is not just changing from a liquid to a gas, even though everybody believes that. Boiling has nothing to do with changing from a liquid to a gas. That's evaporation.
Ow! Oh, you do that! Yeah! It's like a little. It's right here. There you go. Yeah. There's no.
All right, if you will, look at number 33. All right, same system we're working with. All right, liquid plus heat yields vapor, evaporation. The question's asking you, suppose temperature is increased. Okay? How does the final value of each of the following compare to its initial value? The answer is higher, lower, or remains the same. So how would the rate of evaporation change if you increased the temperature? I don't want you to yell out the answer. I want you to do A, B, C, and D on your own, and then I'm going to ask you. Okay? I'm only going to give you about 60 seconds to answer those 4 questions. A, B, C, and D are 4 questions. If you increase the temperature, how does the rate of evaporation change? You're right on the worksheet. Okay, it's too small.
I know, we'll see what can I give you time then what? To go to the bathroom?
Can what?
Can I go to the bathroom?
When are you eating with me? Second lunch or third lunch?
Second.
Fabulous.
Yes. That was
All right, got them all done? All right, so A, if I increase the temperature, what happens to the rate of evaporation, Eric? It is higher, it's going to increase. What happens to my rate of condensation, Trent? It increases, because if the rate of evaporation goes up, we make more what? Let's see, the final concentration of vapor molecules, Emma. What happens to the final rate of vapor molecules?
The rate is higher.
It's higher. Because if you evaporate more, what do you make more of? More vapor, right? So if you make more vapor, you do what more, Trent? What'd you just say? You condense more. So what happens to our final number of liquid molecules there, Ellie? There will be what? There will be less. Because they did what? They turned into what? They turned into vapor. Are y'all with me or no? People answered me right, but I still feel like y'all are not with me.
Not all of us. I said it will.
All right. Now, if you told me that evaporation will increase, that means the water turned into what? It turned into vapor. If you turned into vapor, what has to happen to the water? It has to become what? Less. Remember, this is a closed system. The amounts have to stay the same. So if I turned into vapor, my water had to do what? Decrease. It had to go down. If my vapor went up, the water went down. All right, number 34. I'm asking you how you get these things. Would you increase the temperature or would you decrease the temperature? I'm going to call them for different people.
Wait, what?
And number 34, I'm asking you, do you increase the temperature or do you decrease the temperature to get those things to happen?
Miss Law, how do the clouds turn white?
How do the clouds turn white? They just are.
Or like gray sometimes?
Isn't it just the way
Not a
the
clue.
sun hits it?
Don't teach weather. That is so far out of my area of expertise, I have no idea. I can tell you that lightning comes from the clouds rubbing together because of static electricity. Beyond that, know nothing about clouds. I can't even tell you what kind of clouds they are. Yeah. I can tell you cumulus clouds, but I couldn't recognize what it is. I thought they were fluffy ones, but beyond that. The last time I had our science, I was in 7th grade, and I'm 47 years old, so, I'm a little far removed from that. In order to increase your rate of evaporation, would you want to raise the temperature or lower the temperature? Then that's what I'm asking for. You would want a higher temperature.
Wow.
That's right.
That's what I was doing. I erased it.
No, that's a
How about we? One day right there.
What was that to be? No, really? Really? I don't know about
Alright, so, hey, how do I get an increased rate of evaporation? Tim, what would I do? Would I increase the temperature or lower the temperature? Increase is right. How would I get more vapor? A final concentration of vapor. More vapor, Salma, what would I do? Very good. Alright, I want an increased rate of condensation. I want more condensation. What would I do, Alicia? Increase is right. I want more liquid. I need more liquid in my container. What would I do, Destiny? She's just praying I go away. Like a puff of smoke that vanishes in front of her eyes.
Which one we on?
We're on D. I want an increased rate, an increased number of liquid molecules. I was reading the wrong one. I want more liquid in the container.
So it's gonna go like down or like.
I want more liquid in the container.
Okay, so it's gonna decrease.
Yes. You gotta lower the temperature so less evaporates.
Yeah.
That's what I'm gonna say.
Oh, well, this one.
I can tell. What if it freezes, then we won't be evaporating and condensating. Good, we could have done this with melting and freezing. We're just doing it with evaporating and condensing. No, the state is only gonna ask you about evaporating and condensing, so we're not gonna do it with melting and freezing. Okay, and I will limit myself to this. All right, so we're gonna talk about boiling. All right, we need the same information to talk about boiling. Okay, understanding equilibrium is how we talk about boiling, because boiling is about equilibrium. Now, before we even talk about how you reach a boiling point, all right, some basic differences between boiling and evaporation, first of all. Since I talked about this the other day, all right, where did I tell you that evaporation took place?
The surface.
All right, evaporation is always at the surface. And boiling is generally going to be at the bottom of the liquid. All right, which one has bubbles?
Boiling.
I know that, yeah.
This one has no bubbles. Which one's going to have a higher temperature?
Boiling.
That's probably good enough for the time being.
How long do the next day?
I typically use 5 in physical science, but that's good enough for right now.
Funny.
All right, we caught up? It's okay. I have all day. No, I was being sarcastic. Are we caught up? All right, so we're going to talk about boiling point today. All right, boiling point is the temperature at which the atmospheric pressure is equal to the equilibrium vapor pressure. Okay, it's the temperature at which atmospheric pressure is equal to equilibrium vapor pressure. Now, there's 2 pressures in that definition that we've really not spent a lot of time talking about. Okay? One is specific to just boiling point for us today, and that's equilibrium vapor pressure. Atmospheric pressure, we've talked a little bit about or alluded to, we haven't done a ton with. Okay? So, first of all, what is atmospheric pressure? Basically, that's good. All right, it's the pressure exerted by the atmosphere around us. Okay? So when we inhale, exhale, the pressure exerted on our lungs is atmospheric pressure. Some of you who are more sensitive may notice that some days it's easier for you to breathe than others. All right? Some of you may be bothered by humidity in the summertime. Okay? Atmospheric pressure changes depending on where you're at. We're going to talk about that in a little while. Atmospheric pressure is not the same all over the state of North Carolina. Pressure varies from the coastal region to the Piedmont to the mountains. Therefore, boiling point is going to change between the coast, the Piedmont, and the mountains. Salma.
Do you ever get like when you do something like let's say you just go up the steps or you get up off the couch and you like start breathing so hard?
That means you're out of shape. I'm an old fat white woman, so yeah, sometimes I have that trouble, but I try to exercise a little bit more. Yes. You should not have that problem at your age.
I have it. Like,
You need to exercise more.
when I get up to the bed or the couch.
You really need to exercise more.
Sorry. Especially when I go up them steps.
Okay, you need to exercise more.
I don't know.
All right. Now, equilibrium vapor pressure, I'm going to explain with an example. So I got to draw a really tacky picture. Y'all going to have to work with me. All right. Now, I'm not going to boil water. All right. So let's say that we are going to boil some water at home. We're going to make some spaghetti tonight for dinner. We got to boil some water. All right. So when we go to boil our water, all right, everybody knows, or I'm sure most of you probably do, you can set the water on a lower temperature, but if you're like me, you're probably in a hurry and you put it on high. All right, as soon as you turn it on high and the burner comes on, heat is applied to the bottom of the pan, right? The heat automatically transfers heat to the water, correct? So the water molecules begin to move, okay? Yep. All right, so the water molecules move. Again, when enough kinetic energy, they're going to break the surface and evaporate. Okay, so put some cool air up here. So when these water molecules hit this cool air, what happens to them? What happens to those hot water molecules when they hit those cool air above that pot? Because this is not a closed system like it was in our earlier example. What do they do when they hit that cold air? They condensate, okay? Some of it is going to fall back into the pot, and some of it's going to land where? Outside on the stove. And I don't say to put your hands on the hot stove, but if you actually felt along the edges, it's going to feel how?
Wet.
Wet, okay? Because not all of it's going to land back in the pot, okay? So, some water will condense back into the pot. All right, and I'm going to use an arrow. All right. And you don't necessarily have to do it this way, but this pressure exerted above the pot by the vapor molecules in equilibrium with the liquid is called equilibrium vapor pressure. And I will let you catch up before I keep writing. All right, so there's going to be a pressure above the pot. It's going to be exerted by those gas molecules or vapor molecules in equilibrium with the liquid.
Is that those big booms in there?
Is that how what?
Big, like, no water system bowl, the bowl, so,
It's going to get there. We're just not there in our explanation yet.
Thanks, y'all.
Yeah.
I go to the bathroom.
What is it with y'all? I've been drinking water all morning and I have not gone to the
Can I
bathroom in the
go?
middle of class.
Oh, yeah.
Do you have any hall passes
I
left?
have 2.
Your bladder
Glad
is
y'all- My bladder has managed to,
excellent.
your bladder's
You have a
special.
good bladder.
It's not special. I need to manage to have 2 children and not have to go to class.
How long do I have been here for lunch? 10 minutes.
10 minutes.
My time is late. That's all.
All right, we caught up?
No.
All right. So this pressure right here is called equilibrium vapor pressure. Now, where'd my pen go? As the water heats, more particles evaporate. All right, so if more particles evaporate, what's going to happen to that pressure above the pot? If more particles are evaporating and forming up here, what's happening to this pressure? That's right. Pressure above the pot increases. Okay? Are you with me on that? Yes or no? Okay. You say so.
I'm not with you.
Can you agree with me that as the temperature heats up the pot, Salma, the water moves faster?
Yeah.
As it moves faster, it's going to evaporate faster. Yes or no? Okay. As it evaporates faster, more particles form above that pot. All right. More particles means more pressure. That's all I'm saying. Okay. So if I get more pressure above this pot, that means my vapor pressure is going up. That's all we're saying. Okay. Now, when vapor pressure pot equals atmospheric pressure in the room, water will boil. Now, is that the same pressure every day? No. Atmospheric pressure varies every single day. If you watch the news or the weather or check your app on your phone, you will find that pressure does not stay the same. Water boiling point is 100 degrees Celsius. It is an average. It is not an absolute. So if I choose to do the specific heat lab, and I've not decided for any surety here, but if I choose to do that lab, then when you measure the boiling point, it will probably not be 100 degrees Celsius. It will depend on atmospheric pressure. because the pressure above the pot has to equal the pressure in this room before you see those rolling bubbles. Okay? Until those two things are equal, you're not going to see those rolling bubbles. It might be at 98 degrees Celsius. It might be at 102 degrees Celsius. It depends on atmospheric temperatures or pressures. Everybody got it? Now, let's say that I draw a really tacky map. Alright? So, what?
You ever gone to the bottom of the pool, like all the way to the bottom, and you feel like pressure in your face?
Yeah.
She said she didn't know that was pressure.
Yeah, it's the pressure of the pool. The water's pushing on you. Now, where would we have the greatest pressure?
Mountains.
No,
Did we draw that?
Yes. All right. Greatest pressure is never in the mountains. It's always at the coast.
Why is it harder? Why is it harder to breathe when you're like up higher?
It's just thinner air. Shh, guys. Shh. I don't need to hear your personal anecdotes about breathing in the mountains. Now, because I don't. Lowest pressure is always in the mountains. Greatest pressure is always at the coast. Now, based on that, how would this affect boiling point? Where would the greatest boiling point be? That is right. The greatest boiling point, or let me say highest, the highest boiling point is going to be at the coast, where the greatest pressure is. That means, where's the lowest boiling point going to be? That's right. Now, have any of you taken the foods class? If you bake anything, have you ever noticed the side of the box that talks about elevations? All right, what does it say? If you're over 3,500 feet, it says bake longer, because when you cook at a lower temperature, you have to cook it what? You have to cook it for longer times. Here, because it's cooking at a higher temperature, you cook it for what? Shorter amount of times. Have you ever gone home, you wanted a pizza, it says to cook it for 16 to 18 minutes at 375, and you're like, man, I'm hungry. What's the first thing you're thinking to yourself? I can cook it at what? Higher temperature for what? It cooks faster. So if it cooks at a higher boiling point here, I can cook it for less time. If it cooks at a lower boiling point, you have to cook it longer because it cooks slower. Food cooks slower in the mountains because it cooks at a lower temperature. It cooks faster at the coast because it cooks at a higher temperature. That's because it has a higher pressure. Questions? Anybody? Huh? Piedmont's going to be in between. Okay, it's just in between. Our elevate, we're at somewhere around 900, between 800 and 900 feet above sea level. So we're in between. We're sort of in between. Okay?
Are we done taking notes?
Yeah, I don't think we have time to do the graph. All right, so for homework, you need to study and be prepared for a what?